Hi, everyone. So I'm going to be talking about hydrodynamic escape from exoplanets. And we've heard about this already at the meeting. This is a little bit out of order because of some scheduling, but I will be talking a little bit about magnetic fields, but hopefully this will help as a lead into the discussion of magnetic fields in the rest of the session. So hydrodynamic escape from exoplanets. Why do we think it's happening? So first of all, there's several lines of evidence from the population of exoplanets that substantial atmospheric escape is happening on many planets. One potential signature of this is what's known as the hot Neptune desert. There are very few Neptune-sized planets very close to their host stars, and this has been interpreted as due to these planets catastrophically losing their atmospheres. The atmospheric evaporation valley, which occurs at smaller sized planets, super Earth sized planets, so planets larger than Earth but smaller than Neptune, has also been interpreted as the result of atmospheric escape. So this is also orbital period versus planet size, but unlike in the previous slide where we were looking at Earth's versus Jupiter's and seeing a lack of Neptune's very close in, here we're looking a little bit further out at just smaller sized planets at several Earth radii. And you can see in the population of planets a gap that has been interpreted as evaporation of atmospheres of about 1% the mass of the planet. So in that valley, evaporation occurs quickly. And this is actually a victory for theoretical prediction. There are a few of those, so I always like to point that out. This was predicted by two different groups before it was observed. You can also look at the amount of gravitational binding energy that you expect for the atmosphere of a planet. And compare it.
For 1 minute in and out.
Sorry, someone's not muted. And compare it to the integrated expected heating from high energy photons for these planets. And you can see that if you look at the population of exoplanets this way, there appears to be a line that delineates planets with high binding energy and have larger envelopes, and those planets that don't appear to be present, with too high integrated ionizing flux. And those planets there that are in red are actually planets that are thought to not have atmospheres, so they don't contradict this line. And finally, there have been several direct lines of evidence showing that exoplanets are actually losing their atmospheres. So the most prominent one is the Lyman alpha absorption line observed in UV. This is the first observation of Lyman alpha absorption. We've already heard about this in the meeting, showing during the transit of the planet as it passes in front of its star, Lyman alpha photons from the star being absorbed at high offsets from line center. So at the equivalent of plus or minus about 100 kilometers per second velocity offsets. So this is, if you think about escape models, as I talk about in a moment, somewhat mysteriously large velocity offsets, and there are several ideas for why that's happening. Beautiful observations of Lyman alpha absorption have been seen in the blue wing in particular of the line. This is an example from the warm Neptune GJ436b, indicating that there's more absorbing material in this system at blue shifted velocities, so moving toward us from toward the observer from the planet. And there have also now been transit measurements of in optical and infrared lines, hydrogen H alpha and helium 1083 lines, which are beautiful because they can be observed from the ground. And these direct observations of Lyman alpha, as well as H alpha and helium, but in particular of Lyman alpha, directly demonstrate that that gas is escaping from these planets because they show more absorption than would be feasible just from the size of a planet without an extended escaping atmosphere of hydrogen. All right, so those are the basic lines of evidence for atmospheric escape from extrasolar planets. There's still a lot to be learned But it's quite clear that we need to understand these processes if we're going to understand not just the details of the atmospheric evolution of these planets, but also just the basic properties of the exoplanet population. So do planets have massive hydrogen envelopes or not? Why do different planets, have different just bulk atmospheric characteristics? And in particular, because exoplanets are more easily probed, and in particular, their atmospheres are more easily probed if planets are very close to their host stars. If many close-in exoplanets are losing large fractions of their atmospheres through processes that don't necessarily occur to the same degree at larger distances. If we want to take the observations that we have of exoplanet atmospheres and extend them to understanding planets at larger distances, we need to understand escape. All right, so just for the sake of terminology, I'll say there are two classes of escape mechanisms. They can each be thermal or non-thermal. And I bring this up because this is a meeting with multiple communities. And in my experience, sometimes people use these words differently in different communities. So what I mean is there are kinetic processes, that means loss to space of individual atoms. And that can be thermal, in other words, driven by heat, Jean's escape. Or they could be non-thermal, and we've heard a lot about this at the meeting, often mediated by magnetic fields, for example, charge exchange, sputtering, photochemical, chemistry-driven recombination escape, that kind of thing. So the idea, though, is that you need to give an individual atom enough energy to escape. And then there's hydrodynamic escape, which is the bulk outflow of a collisional fluid. And typically when we talk about hydrodynamic escape of atmospheres, we mean thermally driven hydrodynamic escape. And that's what I'm going to focus on. But you can also have hydrodynamic escape that's non-thermal, like Roche lobe overflow, right? If your atmosphere gets big enough that it actually overflows the Roche lobe, in other words, the tidal gravity from the star that you're orbiting becomes stronger than the binding energy of the planet and your gas escapes. That would be hydrodynamic. You could also have ram pressure stripping from the stellar wind. In principle, you could just push off the atmosphere. And you can have collisional erosion, which is typically, which could be important for Earth-like planets. Okay, so for thermal hydrodynamic escape, what we're talking about is a classic Parker wind, even more classic than using the Parker wind model for the stellar wind, because it's actually driven by heat, by the temperature and a temperature gradient and the outflow. So why do you have a Parker wind? If you think about a fluid, isothermal atmosphere, so fluid meaning it's collisional, an isothermal atmosphere, and you try to put a hydrostatic solution on top of a planet, then at infinity, the pressure does not go to zero. And that's bad because then you have a pressure gradient at infinity and that accelerates the gas outward. So, and it drives an outflow. So that's where the wind comes from. The energy in this isothermal version for the PdV work required to push the outflow out comes from this isothermal assumption, but you can make models, of course, that have appropriate heating and cooling that get their energy from actual energy sources and do this as well. So Parker winds flow through a critical point called the sonic point, where unless they are pressure confined from the outside. And that's one of the ways that magnetic fields can play an important role in these processes, is if they provide pressure confinement. So if you're unconfined, then your Parker wind will flow through a sonic point where the sound speed is approximately the escape velocity. And the reason for this is it's essentially similar to a critical point in a de Laval nozzle. For those who may be familiar, that's what got the Saturn V rockets off the ground. And in this case, rather than having the shape of the nozzle in a particular shape that causes the geometry to change and give you a critical point, what's happening is because it's a spherical outflow, the outflow is expanding, and that causes an effective geometry change that requires you to go through a critical point. And just qualitatively, the way to think about this is that as the temperature of your outflow goes down, the distance that you have to go before you go through this sonic point, or in other words, before your sound speed can be approximately your escape velocity, goes up. So the harder it is to stay collisional all the way out to where your sonic point would be, which is an assumption of this type of model. And also your mass loss rate goes down as your temperature goes down. And that's because in a fluid, if your velocity, if your outflow velocity is below the sound speed, then the structure that you get is roughly hydrostatic. Your density is falling off exponentially. And it has to fall off more to get to that sonic point in a lower temperature outflow. So your mass loss rate goes down. All right. So how do you tell the difference between genes and hydrodynamic escape? We've heard several perspectives on this. This is the way I think about it. You need to think about the gravitational binding energy versus the thermal energy at the exobase. And in other words, you have to accelerate to supersonic velocities while you're still collisional if you want to have a hydrodynamic outflow. So sometimes people talk about this from what I think in my, often people from the planetary side, at least in my experience, talk about this in terms of let's figure out where the exobase is and then decide if you have enough energy to escape from the exobase. That's the top up here. From if you're making a hydrodynamic model, often the easier way to do it is to think about the opposite way, and to say, well, let's get our hydrodynamic outflow model, look at that sonic point, that critical point, and ask, is the outflow model still collisional there? But if you look at the math, those are the same thing. So people will talk about it from both perspectives, but it's the same. Okay, but the challenge for this is that the temperature and the escape rate are coupled by the PDV work cooling. So the exobase location depends on where the energy is deposited. And you need to actually understand the heating and cooling and the structure of the outflow before you can actually identify where the exobase is, where the sonic point is, and do that evaluation. Okay, so you have to understand the dominant heating and cooling mechanisms to know if you're in genes or hydrodynamic escape regimes. So the two heating mechanisms that people typically talk about for exoplanets for driving strong hydrodynamic escape are first what's called sorry, my brain is not working. It's too early in the morning. First, you can get your heat from the heat of formation stored in the planet's core. This is called core-powered cooling in core-powered mass loss, sorry, in the exoplanet literature. And essentially, you've collided your solid material together to form your core, and it's just cooling over time. And that, coupled with the boundary condition, a hot boundary condition on the outside of your planet from just the bolometric heating from the star, the bulk heating of the atmosphere, can allow you to drive hydrodynamic outflows from that stored cooling. And the other thing that people talk about, which is more frequently talked about, but that doesn't necessarily mean that it's more important necessarily, is photoionization heating, otherwise known as photoevaporation. So the basic idea here is that you bring in an XUV photon, and it photoionizes something in your atmosphere. So a small fraction of your irradiation energy is coming in XUV photons, but there's a really large cross section for their absorption in the atmosphere. Typically, this happens at about nanobar pressures, so very high up. And at those high altitudes, cooling may be inefficient, allowing energy to go into escape. So then you photoionize, the electrons run around and collide with their neighbors, and you eject heat, and that heat gives you the pressure gradient that drives escape. So just for comparison, in Earth's thermosphere, you have XUV heating that could be similarly described. Of course, it's not hydrogen in that case. But what happens to that heat, rather than driving escape, is that it's conducted lower into the atmosphere to the mesopause, where then the atmosphere is dense enough to radiate away that absorbed energy and carbon dioxide 15 micron emission. So when, again, we need to think about the thermospheric energy balance and trying to understand what's happening in these different kinds of planets. So to give two examples, here on the left, we have Venus, where you see EUV heating coming in at the top of the atmosphere, and that's mostly going into conduction and 15 micron emission. Whereas for the hot Jupiter, HD 209458b, that photoionization heating, a little bit of it goes into radiation of Lyman alpha, but the vast majority of it goes into driving PDV work of the atmosphere. And you can make an outflow model and then look at the gradients in the atmosphere and decide, can conduction actually send heat down fast enough to compensate for the heating rate? And in the cases of hot Jupiters, it cannot. Okay, so just to summarize that, planets can be heated by these high energy photons, and that can cause escape, or it can just cause radiation, which heats the atmosphere, and you could have some genes escape there, but it's not driving this hydrodynamic outflow. All right, so we talk about when we look at these exoplanets, they're observed. People often talk about observed mass loss rates, and I just want to make the point that these are actually model dependent. So because the line center is obscured, Lyman alpha absorption probes far from the planet where interactions with the stellar environment are quite complicated. Because it's probing neutral hydrogen, the ionization fraction and the level populations, which depend on the XUV environment, are really important for understanding what observational signatures you're going to see. So these are two examples of ionization fractions and two different wind outflows. And so you can see that they can vary substantially. The amount of neutrals you see doesn't necessarily tell you the whole story. So, and because the outflow velocity is set by about that sound speed, which is about 10 kilometers per second for hot Jupiters, and it can be even less if you have a less deep potential well. That obscuration at the center of the line prevents you from probing directly the outflow velocity. And so you're really looking at something at large scales. So I'm actually going to skip through this because I'm going a little bit slower than I intended. My brain isn't working this morning. Okay, so I can come back to those other probes if people are interested. So why is Lyman alpha absorption? Lyman alpha absorption is seen around some planets, but it's not actually seen around others. A number of observations have been done looking for Lyman alpha. And so we need to figure out—
2 minutes left.
Yep, thank you. We need to figure out why you can see things at those high velocities in some cases and not others. And here's an example of a photoionization-driven outflow from a hot Jupiter, where you can see that in the middle and the right panel, where the stellar wind is actually interacting with this planetary outflow, at large distances from the planet, it accelerates material to observable velocities. Whereas on the left-hand side, where there's no stellar wind outflow, then it's not causing that acceleration. So in this particular kind of model, the basic physics of Lyman alpha transits can be understood this way. If you look at a top-down view on the left and on the right, a side-on view of the orbital plane of an outflow, and you have stellar wind or radiation pressure radially accelerating your gas coming out of the planet, then you see material coming out of the planet, and it gets progressively ionized by the stellar EUV flux as it moves along the tail. You have competing processes here. High EUV flux drives a more powerful outflow, but ionizes the neutral hydrogen tail faster. And so then the question is, which wins? And you can do a calculation of this, and we've done this, and you can see that, and you can actually predict whether you're going to see an absorption in Lyman alpha or not, based on that balance. And essentially, you need to radially accelerate the gas into the blue wing. And what this means is that the launch velocity of the outflow, which tells that the fundamental observable quantity in the Lyman alpha transits is the typical time for a neutral hydrogen atom to travel before it's photoionized. Which is a measure of the launch velocity. And it turns out that the actual density of the outflow, how much material is flowing out, only comes in the log. And it does not so you're not measuring the mass loss rate per se, but instead you're measuring the outflow velocity. All right. So I'm going to, because I have, my apologies, I've run out of time. I'm going to stop on this slide and I'm going to make some comments that are relevant to what we're going to be talking about today, which is the role of magnetic fields. So first of all, there are a number of different processes that could matter at large distances. So there's radiation pressure, which is on the left here. Radiation pressure can play the same role that I described for the stellar wind in pushing the outflow. Sometimes, so in the community, there are two kinds of models that people make. One of them is collisional fluid models, and another one is kinetic models, essentially. And the key thing here is that the fluid outflows are highly ionized. As came up the first day, actually, you know, the densities in these outflows are quite a bit higher than the ion density in, for example, Jupiter's magnetosphere. So there are a lot of ions running around, and they are quite collisional. So there's a subtlety in that we're looking at the neutral ions, and so you have to ask, are the neutrals actually well coupled to the ionized outflow? But for the most part, they are. So you're acting as a fluid as you move out. As you move out to larger distances, when you interact with the stellar wind, you can have charge exchange at that boundary to produce high velocity neutral atoms. So that is another alternative for how you can get things at those large velocity offsets if you don't want to accelerate them with the wind. So so I told you that we can predict you know, whether you get absorption or not, depending on whether you're using this wind acceleration model. But charge exchange is also successfully predicted those high energy, that high velocity absorption. And this is something that needs to continue to be, the trends need to be tested against each other for these two models. And finally, magnetic fields, which is again the topic today. So how do we think about magnetic fields in this context? So there's a ton of ions, and so you can have magnetic fields. So what's going to happen? So I'll just go to my last one more thing. So first of all, if the planetary magnetic field is strong, it can reduce the outflow from the planet. Essentially, you can have a dipole.
I'm sorry. I think it's time to go to the question and answer
two more
section.
sentences, please. So you can,
yes.
Yeah. So you can confine the outflow into a portion of the magnetic dipole, and the way to tell that is by comparing the magnetic pressure of the planet's field to that of the outflowing wind. But you'll still get an outflow along the poles. And if your outflow is coming out along the poles, then you can think of an effective Alfvén radius, similar to, you know, what we think of as an Alfvén radius of the star, except there's a key difference here, which is when you get to the Hill radius or the Roche-Loeb radius, where stellar tidal gravity starts kicking in, then it is extremely difficult for the planet's magnetic field to keep hold of that material. And so it starts turning the wind into that tail shape, even with quite strong planetary magnetic fields. And so you can end up with this large scale outflow structure, even if it's not coming uniformly from the planet, as I described. Now, the one exception is if you have a very early time, very strong field from the star that can essentially hold the outflow into place and mass load directly onto the magnetic field from the star. The densities of these things are higher than you would normally expect in this region. So you actually have to have a quite strong field, but you can have quite strong fields at early times. Okay, I'll end there.
All right, so we do have one question in the chat, and if other people have questions, please raise your hand or put it in the chat. So the first one I see is from Ofer Cohen. Do the results you showed suggest a much smaller mass loss rate than typically assumed?
Oh, no. The mass loss rates that are typically assumed are, okay, so it depends on the strength of the magnetic field. The mass loss rates that are typically assumed, I think, are probably correct, unless the planetary field strengths are very strong. That may be the case for hot Jupiters, which if you use correlations of magnetic field strength with the energy flux and expected energy flux through the planets, then for hot Jupiters specifically, you may have lower mass loss rates than are typically assumed, but yet still see those Lyman alpha absorption signatures. However, for lower mass planets, it's actually quite difficult to match the demographics of that evaporation valley, for example, if you have strong magnetic fields. So it looks like, at least at early times, the very strong fields that would reduce the mass loss rates dramatically tentatively look like they may not be there for the lower mass planets.